Welcome back to differential calculus class. So we are still on partial derivatives. In this class, we'll be discussing second order partial derivatives. So let's start. We are going to start with notations for second order partial derivatives. So you will recall that if we assume a function z equal to f of x and y. In this function, we have the dependent variable z and we have the independent variable x and y. Now, you also recall that in the first order partial derivative, we are asked to find partial derivatives or what is meant by first order partial derivatives. If the question says find the partial derivatives, so indirectly we are asked to find first order partial derivatives. But if it's going to be any other partial derivatives, the question is going to indicate that now it's giving us the partial derivative of z with respect to x. If I want to derive the first, what if I want to derive the second order partial derivatives from this first order partial derivatives? Because the way it goes is that the second partial derivatives is going to be derived from the first partial derivatives, while the third partial derivative is going to be derived from the second partial derivative. So and it goes like that. So this is our first order partial derivatives. Now, if we are to derive the second order partial derivatives, so what we are going to do is just to simply find the derivative of these first order partial derivatives. In other words, we are going to have the the partial the partial derivative of z, the partial derivative of x. So we are going to redifferentiate this. So we now have the partial derivative of z with respect to x. So here we are going to have the derivative of this first order partial derivative with respect to x. So in other words, this is equivalent to saying we have this square z and this x square. So in other words, what we have here is that we have second order partial derivative. So this is one of the notations we use to represent second order partial derivative. So another notation we use, this one is respect to x. Another notation we use is we can use this z sub with x. So this also refers to our second order partial derivatives. What of situation whereby I want to find the partial derivatives of z with respect to y? You will recall that the first order partial derivative of y is given as the partial derivative of z with respect to y. Okay, now if you want to find the second order partial derivative of this, so what I'm going to do is that I'm going to redifferentiate these partial derivatives. So in other words, I'm going to have the partial derivative of z with respect to y, then dy. Okay, so in other words, this is equivalent to saying the partial derivative square of z divided by partial derivative divided by dy squared. This is the second order partial derivative of y. So another notation we use is we can just use z, this letter, then we have y. So, because zy means first order partial derivative, while zyy means second order partial derivative of y. So the same thing applies to zx means first order partial derivative of x. Then when we have zxs, it implies second order partial derivative of x. So this is about notation. It's about notation we use for second order partial derivatives. So on partial derivatives, so we want to talk about second order partial derivatives in this class. So we want to take this example. Have this example before us. We find the second order partial derivative of z equals 7x raised to the power 3 plus 9xy plus 5y raised to the power 5. So how do we solve this problem? Solution. So let's rewrite the function 7x raised to the power 3 plus 9xy then plus 5y raised to the power 5. So you remember in our previous video that you were told in order to find a higher order partial derivatives, you need to first find the preceding order partial derivative. What do I mean by that? In order to find second order partial derivative of the function, you must have found the first order partial derivative, because it's the first order partial derivative you derive second order partial derivative. Without first finding first order partial derivative, there is no way to derive second order partial derivative. Now, you remember that we can use z suffix x to represent the first order partial derivative of z with respect to x. So if that is the case, so let's find it. The first term here contains the relevant variable, which is x. So we are going to differentiate that. So how do you differentiate this? You apply power function rule. So you bring down the power 3, you multiply by the coefficient, that is 3 times 7, you have 21. Then you write x. Then 3 minus 1, you subtract 1 from the power. So we have 21x squared. Then you have plus. You move to the next term. The next term also contains the relevant variable, it is x. So you apply multiplicative function rule here. So you are only concerned with the relevant variable x. So while you hold other term, the other element in that component constant. So what we have, we differentiate x. When we differentiate x, so it gives us 1. So we have 9 times 1 times 9. 9 times 1 times y. Then we have 9y. The next and the last term does not have the relevant variable x, so we ignore it. So this is our first order partial derivative of z with respect to x. Now that we have found the first order partial derivative of z with respect to x, we can now proceed to find second order partial derivative of z with respect to x. So if I denote that with zxx, so what I'm going to do is that I'm going to differentiate this first order partial derivative with respect to x. So if I do that, so the first term here contains the relevant variable x. So I'm going to differentiate this component, multiply it by the coefficient 2 times 21, that is 42. Then we write x. Then you subtract 1 from the power. So 2 minus 1 is 1, so it's 1. So we don't need to write it. This is our second order partial derivative of z with respect to x. If you look at this, the last time we learned does not contain x, so we ignore it. So now, what of the second order partial derivative of z with respect to y? So in order to do that, we first need to find the first order partial derivative of z with respect to y. So this gives this. So this first term here does not contain y, so we ignore it. Becomes 0. So here it contains y. So we are going to apply multiplicative rule. So meaning we are going to differentiate the relevant variable only while we hold other element constant. So when we differentiate y, it becomes 1. So we have 9 times x times 1. That is 9x. Then you have plus. Then the next term contains the relevant variable y. So we are going to differentiate that 5 times 5, that is 25. Then we have y. Then you subtract 1 from the power, 5 minus 1, that is 4. Then we have let's find the second order partial derivative of z with respect to y. So what we are going to do is that we are going to differentiate this with respect this first order partial derivative of z with respect to y. Now with respect to y again. So here this first term does not contain y, so we ignore it. Then we move to the next term. It contains the relevant variable y. So we differentiate that. So we are going to have, we multiply the power by 25. 4 times 25, that is 100. Then we have y. We subtract 1 from the power. 4 minus 1, that is 3. So this is our final answer. So you can try this on your own by finding the second order partial derivative of this function. So we have 3x raised to the power 3 plus 5x squared y raised to the power 3 minus 4y raised to the power 4. So find the second order partial derivative of z with respect to x and also with respect to y. And drop your answer in the comment section. Thank you.